Now let's look at another case. Also, a system with more than one block. Let's say we have a slope again. This time the angle is theta, and here's a pulley, and we have a rigid string with no friction with respect to the pulley, and we have a block here. Let's name M of 1. It is connected to a spring, fixed on the ground, a spring constant K. Initially, let's say that the spring has a length of 20 cm and no stretch to the spring and no compression. And the other end of string is connected to a block of mass M2. Let's first consider there is no friction between M2 and the slope. What we're going to do is we're going to actually pull this M2 down by 20 cm. So when we pull this down 20 cm, then this block M1 will go up to somewhere here. And it will have a height of, because this go down 20, so this will go up 20, so it will be 40 centimeters above the ground. Our question is, obviously when we let go of or pull this M2 down 20 centimeters on the slope, we let it go, M2 will move up and this one will come down. Our question is, when the block M1 goes down back to this 20 centimeters line, what is the V of both block? So again, it looks like system defined as M1 plus M2. When can we define two blocks as one system? When they have the same rate of acceleration, same rate of speed, then we will find. So we can define M1 plus M2 because they behave like one mass. Does that make sense to you? If they have the same rate of acceleration, same rate of the speed. Okay. So we again need to mark all the forces. The internal is non-frictional again, no friction here, no friction. The external here has a Kx force, and also it has M1G. So for the block of M1, T is internal, external is M1G, and the force Kx from the spring. Both are external. And for this one, M2G is external, normal force is external, but that tension T is internal. So therefore, out of that M1G, Kx is external, Fn, M2G external, and Fn is the only non-conservative. So we say sigma W non-conservative equals to only one non-conservative, which is Fm. That does zero work because displacement S is perpendicular to the normal force. So again, we say mechanical energy changes zero, system mechanical energy is conserved. So let's think about change. Change of kinetic. Initially, we pull M2 down here, so M2 is zero speed, M1 zero speed, so initially it's zero. But final seems like the question is, when this one goes back to here, this one goes down to the initial 20 centimeters line, what's the V? So it is actually M1 plus M2 of V squared minus zero. That's the change of kinetic because both blocks should have the same speed. And then initially the spring has been stretched because this is a position springs at its original length, but since this M2 goes down, M1 goes up, so initially spring has been stretched by 20 centimeters, but finally when this one comes back and the block comes down here, spring has no potential energy, so the final minus initial is 1/2 K of that 0.20 squared. That is the initial displacement. And then change of gravitational potential energy. Let's talk each of them independently. That obviously M1 initials here, if I know here, it goes down. So it's minus M1G of 0.20. It goes down this much. For this one, initially it's here. Now it goes up the hill. So that one's a plus. Plus M2G. How much it goes up? If it moves up of 0.20 meters along the slope, and then delta H, we can get it from the 0.2 times sine theta. So that is 0.20 slope distance times sine theta. That is how much higher M2 get. So M2 gain gravitational potential, M1 drops, because when this one starting from it goes up, this one goes down. So that term is change of gravitational potential energy. That equals 0. Let's examine. Our question is find the V. We know everything else. Mass, we know. Spring constant should be given. And G is a constant. And angle is slope. And we can find that. Obviously, one more add on. If we do have a mu K between our block of M2 and the slope, and then when that happens, when M2 goes up by 0.2 of meters, that's displacement, and friction is this way, Fk is that way, and this M2G can be split again by this M2G of cosine theta, and that down the hill is M2G sine theta. And M2G cosine theta is balanced by Fn. So again, we say now if we add one more of external force, which is non-conservative, then the work done is negative Fk time displacement is 0.20. That equals to our change of, we can fill in the same term, change of our delta Ke plus change of our delta Ug plus change of U of elastic. That is the delta of Ke turn. That is delta of U elastic, delta of U of gravitational. And we can just put Fk is mu k times normal force, and normal force equals to M2G of sine, cosine theta, because M2G cosine theta equals to Fn. So, and time 0.20. And this term is here, because we replace Fk is mu k times normal force. And because of the involvement of Fk, we expect the final speed will be smaller than the non-friction case. Okay, let's look at another example. That is, if we have a block right here, position A, there is no friction between the block and the slope. Well, let's say the block never lose contact with the surface. So if we mark, we always mark that Fn. Fn means there is a normal force. That's a contact force. If the block always follows the contour, then Fn is always perpendicular to any small movement of ds. Therefore, we say that Fn dot ds equals to 0. That means Fn doesn't do work. This is a case of a one block case. So every single force is external force. There are two of them, Fn and mg. So, well, since Fn is non-conservative force, doesn't do work, so we can safely apply conservation mechanical energy to this block. Our question number 1 is, if we want this block go down and being able to reach the top of this circular path of radius r, how high the initial h should be? we can imagine that if this H is really low, if we start our block somewhere even below that point C, certainly it will not go up to point C. So not only we should set the block at the point C, maybe it has to be a little bit higher than that. So we have to figure out H is more than 2R or equal to 2R. If it's more than, how much more? So we want to know that how high the initial point A has to be, then the block will be able to reach C. Reach means at that point it is virtually lose contact. That is being able to reach mean, because it's barely reached there. Okay, so when the block reaches here, guess what? It almost lose contact. So the only force on the block is mg now. But don't forget, because it moves, it has a velocity at here, v. Let's name v of c. It has a velocity because it does circular motion. Everything does circular motion must have a centripetal acceleration. It must have a tangential speed, right? So since we're going to able to apply conservation of mechanical energy, we say at point A, let's take this as h equals 0, the ground as h equals 0. So at point A, that is mg of h. At point C, that is 1/2 mvc squared, because it has kinetic energy, is moving, the block is moving, plus mg of 2r, because point C is 2r above h equals 0 line. Now this is the equation we have problem, because initial h is unknown and vc is unknown, so we cannot solve it. But there is a clue that the block at point C does circular motion, and it is virtually lose contact with the track. So we say mg is the force centripetal that helps the block of that centripetal acceleration of vc over r. Remember, everything does circular motion must have centripetal acceleration. If you have acceleration, you must have at least one force, and right now that force is mg. So by listing mg is the force that creates centripetal acceleration for the circular motion of the block at point C, we have a relationship, because actually you can see we can, from here, if we time 1/2, we time 1/2, and both sides times r, we can get 1/2 mvc squared can be replaced by 1/2 mgr, right? Because you see if both sides times by r. So we're going to replace that term. So left side is mgh, and the 1/2 mvc squared term can be replaced by that 1/2 of mgr term, because that is from here. Okay, and then the next term is mg2r, so it's 2mgr. So from there you can see mg cancels, mg here, mg here, mg here. So it looks like h must equals to what? 2.5r. Isn't that interesting? We have to let go of the block. 2.5r, not 2r. If you let the block go at same height at this point, it's not going to be able to make it. It has to be 2.5r somewhere here, and then the block will be able to reach the very top and lose contact. So that is question 1. Question 2. Let's say we released our block at initial height of 2.5r. When the block reaches here, which is point B, what is the normal force on block B? Well, obviously, normal force right now, let's mark Fm prime, is perpendicular to the displacement, because the block right now, the displacement ds is tangential up. So that's that. Well, since that we know, look at this picture. Actually, if we want to draw the free body diagram, there is one more force, which is mg. Mg is always there. at location B, mg is down, Fn is point to the center of the circle. So Fn, let's make Fn prime because it's different than Fn here. Fn prime is responsible for the circular motion at this moment. At this moment, V is Vb. Vb squared over r is the centripetal acceleration at this moment. So Fn prime is responsible to provide the block with the centripetal acceleration of Vb squared divided by r. And we need to find Vb. Obviously, from A to C, mechanical energy is conserved. From A to B, mechanical energy is also conserved. So from A to B, delta ME equals to 0, which means mechanical energy is conserved. When that happens, we say initially we have what? We have mg of 2.5 r, because that's where we start. At point B, we have 1/2 mvb squared, that is kinetic energy, plus the height. Right here, we are 1 r above the h equal to 0 line. So the mgr, that's gravitational potential. So we can solve. What do we want? Actually is that this combination. So why not let's have this r being divided by every single turn, and we will have both sides times by 2, so we will get this mvb squared over r. Look like what? This r cancel, that r cancel. At both sides, well, here's 2.5 mg, here's 1 mg, so left side is 1.5 mg left. Both sides times by 2, that will be 3 mg. So the result is Fm prime equals to 3 mg, isn't it? That's very interesting.